Hello, everyone. Welcome to today's lesson on redox reactions. So electrochemistry is something that is very common everywhere. In fact, living cells perform redox reactions to extract the energy from sugar. Essentially what happens is when you eat sugar, the sugar molecules disperse and enter the cells. And once inside the cells, there's an elaborate system that strips electrons from those sugar molecules and then uses the negative charge in those electrons to concentrate positive ions on one side of a membrane inside an organelle called the mitochondria. And those electrons, the negative charge, using to build up that positive gradient of hydrogen ions inside the mitochondria, those particular reactions generate energy in the form of ATP in the cell. And the generation of the ATP during a cycle called Krebs cycle, all based on electrons being transferred like hot potatoes from one material to another. And that energy, again, is tapped to form the energy currency of cells. So we also, of course, use electrochemistry in batteries, and batteries are basically found everywhere. We've all become slaves to our technology, and our phones have very efficient electrochemical reactions going on that create the flow of electricity through external circuits that enable them to work, these devices. So here's an example of a car battery here. And the car battery has two electrodes. One is lead oxide. And the electrons flow through an external circuit from the lead electrodes to the lead oxide electrodes. And of course, we all know how important that is to start your engine of your car, to turn your lights on, to make your radio work and your music devices. Now, the car battery is in fact a battery. It's made up of 6 2-volt cells. And when you connect those in series, you get a total of 12 volts. There's a significant amount of electricity that can flow out of a car battery, so they're not to be taken lightly. They also have an electrolyte of sulfuric acid, which is potentially very hazardous, so you need to be careful. In fact, modern times, they seal the batteries so that the sulfuric acid can't explode out of there and hurt the person trying to charge the battery. So that's been a major improvement. Now, there's an oxidation reaction happening, which essentially is the name of a chemical reaction where electrons are lost. So the lead atoms in the lead anode lose electrons, and those electrons travel through the external circuit. And when they get to the lead oxide cathode, those electrons are used to perform another chemical reaction called a reduction. The electrons are gained. So typically we show this reaction. We put the oxidation first. We use 2 lines. And then you can see here the lead is going to an oxidation state of +4. And I'll get to that in a minute. We'll talk about that. So the first primitive batteries for cars were made, well, even before cars, of course. But cars didn't appear until the 1900s, but 1700s. And they simply took stacks of metal and put barriers in between that were non-conducting, and noticed that there was electricity that was flowing from these concoctions that they created. So, and they used an electrolyte of salt water to accomplish their goal. So here's a standard cheap cell that you would buy at any dollar store. Although from my own personal experience, these don't last very long. So remember one time I bought some for a camera, maybe 10 years ago, and I took about 5 pictures and the batteries were dead. So I realized dollar store, sometimes the products are available, but they're not quite as effective as some of the other products on the market. So here we have, you can see all the different parts to this battery. We've got mainly what I want you to focus on is the zinc anode here. And we have an electrode here that's made of graphite. So essentially, let's talk about what is happening. The electrons are released when the zinc atoms in the anode undergo a release of electrons, and zinc atoms let the electrons go, and when they do, they form zinc ions. And of course, the electrons flow through an external circuit to do work for you. And when they arrive back at the cathode where the reduction occurs, the electrons cause a chemical reaction to occur. In this case, we have an ammonium chloride, zinc chloride, manganese dioxide paste, and the ammonium ions are reduced by gaining 2 electrons into ammonia and hydrogen. Then, of course, we have to use the hydrogen up somehow. So the hydrogen, or else the battery or cell in this case could potentially explode. So the hydrogen gas is then to perform another oxidation reaction. The manganese dioxide is oxidized to manganese 3 oxide and water. So a simple way to remember the 2 different reactions here. We can use a little saying. Leo the lion says grr, where Leo stands for loss of electrons, means an oxidation. Gain of electrons means a reduction. So we can have here a gain of electrons, reduction. Now, you never try to charge one of these cheapy cells because the hydrogen generated can actually cause an explosion here. So here we have another type of tiny little cell that we can use. Used to use these a lot, and I remember I used to use one in my watch. They're little, tiny little things. There are oxidation reduction reactions going on here again, and the zinc in the anode is undergoing an oxidation. Zinc atoms are changing into zinc ions and releasing electrons that flow through an external circuit. Those electrons then, after flowing through the external circuit, are used to reduce H2O to mercury. And so the electrons basically flow from the zinc through the external circuit, and they flow back to the cathode. In this case, the H2O is the cathode, and perform a reduction reaction at the other end. So now, again, to mention, you can have any chemical entity, an ion, an atom, or a molecule lose electrons. And anything that loses electrons is said to be oxidized. And if it gains electrons, it's said to be reduced. So one can't happen without the other. So if we show you here, here's an example of a half reaction where a sodium atom is changing into a sodium ion and an electron. So how do we know electrons are being lost? Well, let's go and do some simple bookkeeping. We know that sodium atoms have 11 protons and 11 electrons, and a sodium ion has 11 protons but only 10 electrons. So we can see an electron has been lost. So there's another term we also use for a substance that's oxidized. We can say that the substance oxidized is actually the reducing agent. Now, let's couple that with another half reaction. So in this case, we have chlorine gas gaining 2 electrons, forming 2 chloride ions. Again, it's a reduction reaction because it's gaining electrons. And we can, again, look at a chlorine atom as 17 protons and 17 electrons, whereas a chloride ion has 17 protons and 18 electrons. You can see there is a gain of an electron here. So the reduced substance we can also refer to as the oxidizing agent. Now, these 2 reactions happen together. So what we're going to do is we're going to put those 2 reactions together. But you'll note that the oxidation only released 1 electron. The reduction reaction gained 2 electrons. So we have to somehow balance those 2 out. So we're going to balance it by multiplying the oxidation by 2. And now we have 2 electrons lost, 2 electrons gained. We have a balanced situation. So we can combine these 2 equations together and cancel the electrons off of each side. And here now we have an overall redox reaction equation that's balanced for electrons. And that's typically what we'll learn to do in the lesson as we move forward. So electrochemistry is used in a variety of applications, as we've mentioned. Very useful in, we can use solar energy to perform redox reactions, and that's how we convert the sun's energy into electricity. We used to use, in the old days, we used to use film for photographs, and the process where the actual images were created on the film were actually redox reactions. We use redox reactions to clean our drinking water, to oxidize the cell walls and membranes of living things, to kill them. Very useful. Anybody knows who has a pool, if you don't put an oxidizing agent in your pool, like hypochlorite ion, then your pool will start to become alive. It will, you'll get all sorts of algae growing in the pool. And of course, an understanding of redox reactions has allowed us to reduce a natural redox reaction, which is corrosion of things like iron. So here you see some equations showing the reaction, the overall reaction of iron rusting. Iron, of course, to rust requires not just oxygen from the air, but it also requires water. And essentially, you're making hydroxides of iron. Both ferrous and ferric hydroxide are the end products. And of course, we all know that the rust accumulation, it does not have the same properties as iron. It's soft and malleable, and it falls off, and you get pits that form when there's a break in the actual layer that is covering the surface that is being protected. So now, electrochemistry is basically at work everywhere. Now, let's go over some of the rules for assigning oxidation numbers, which can be useful to us when we're trying to determine whether an oxidation or reduction reaction is happening. So these rules are all on page 85 of your book. And after you complete the rules, it'd be a good idea to try an example in your book on page 85 to practice the rules. Some of you might already be fluent in this because we learned this in a previous chemistry course in engineering. But I'm going to go over them again reasonably quickly. So some of the more important rules is any individual atom in a free element is assigned a value of 0. So an example here. So if I have a chlorine atom just existing on its own, its oxidation state would be 0. If I have 2 chlorine atoms in a molecule of chlorine, the entire molecule has an oxidation state of 0. So remember, an oxidation state is really assigned to, it's kind of a bookkeeping thing where we're keeping track of how the electrons are being shared. So in a chlorine molecule, the electrons are evenly shared. Neither of the chlorine atoms are winning the battle for pulling electrons away from the other. So we say that this balanced state, we assign it an oxidation state of 0. So the sum of all oxidation states of all the atoms in a neutral species, such as an isolated atom or a molecule or a formula unit, is always assigned 0. So an example, if I had methanol here, CH3OH, the total oxidation state for the carbon, the hydrogen, and the oxygen in this molecule would equal 0. Similarly, a formula like magnesium chloride, which is an ionic compound, the total oxidation state for both the magnesium and the chlorine is 0. Now, if you have an ion that's assigned a charge, in the case of ferric ion, the oxidation state is always the charge on the ion. So we can have this one here is permanganate. The overall charge adds up to -1, which means if I added the oxidation states of the manganese to the 4 oxygen atoms, it should add up to -1. And we'll go into the rules for individual atoms as we move forward. So now in their compounds, group 1 metals always have an oxidation state of +1 when they're in a compound. Now, if they existed as a pure element, it would be 0. But in a compound, it's going to be +1. And group 2 similarly will be +2. So an example here in potassium chloride, potassium is +1, which would make chlorine -1 because the whole thing has to add up to 0. It's a neutral overall entity. So here in potassium carbonate, potassium is +1, each atom in this formula, and the carbonate is a -2, CO3 2-. And the oxidation state of magnesium here is +2, and here is +2, and nitrate NO3 is a -1. There's 2 of those. Again, the whole thing adds up to 0. Similarly here, bromide is -1. Each bromine atom is a total of -2. Added to the +2 of magnesium gives an overall oxidation state of 0. Now, Fluorine, very high electronegativity, is always assigned an oxidation state of -1. An example here, hydrogen fluoride, the hydrogen would be +1, the fluoride would be -1. In this case, the fluorine would be -3 total. Each fluorine would be -1. So the oxidation state here of chlorine would be +3. In this case, SF6, sulfur hexafluoride, the fluorine is -1, so the sulfur's oxidation state would be +6. Now, compounds that contain hydrogen, almost always hydrogen has an oxidation state of 1. There are a couple of exceptions. For instance, when hydrogen is bonded to less electronegative metals, and all metals have less electronegativity than hydrogen, sorry. So in this case, hydrogen, when it's bonded to a metal, its oxidation state will be -1. Examples would be, I'll get to in a minute, but here you can see hydrogen is +1 in hydrogen iodide, in H2S, in ammonia, and in methane. Again, hydrogen has a smaller electronegativity than all of these other atoms. Therefore, it loses its electron more or less in the electron bookkeeping world and achieves an oxidation state of +1. So in ammonia, for instance, if hydrogen was +1, nitrogen would be +3, or -3 in this case. In this case, it's +1, carbon would be -4. In this case, hydrogen is +1, sulfur is -2. Hydrogen is +1, iodine would be -1. Now, there are exceptions, as I said. Hydrogen can be -1 when it's bonded to a metal that has a lower electronegativity than hydrogen. So hydrogen, in fact, the electron pair tends to spend more time around the hydrogen. So in this case, calcium's oxidation state would be +2. Each hydrogen would be -1. Sodium would be +1. Hydrogen would be -1. Similarly, for potassium hydride, potassium's +1, hydrogen's -1. Now, in its compounds, oxygen almost always has a charge of -2. Again, over here, if you look, group 16 tends to have an oxidation state of -2. When oxygen is bonded to itself or to fluorine, however, the oxygen atoms have an oxidation state that changes. And it can vary depending on the formula. I'll give you some examples here. Now, I want to emphasize these are very, very rare events. Most of the time, oxygen is -2 and hydrogen is +1. But I just want to go over some of the rare exceptions. So for instance, these are all common examples here. Oxygen is -2 in all these examples. And when it's not -2 is when oxygen is bonded to fluorine. Why? Because fluorine atoms have a stronger electronegativity than oxygen atoms. So in this case, fluorine would be -1 for each atom. There's 2 of them. Total would be -2. Oxygen would have to be +2 in this example. Peroxides, again, are another example of an exception. So in a peroxide, oxygen, we're going to defer to hydrogen being +1. Hydrogen only has 1 energy level and it only has 1 electron. So hydrogen can either be +1 or -1. But in this case, oxygen is more electronegative than hydrogen. Hydrogen will therefore be positive, so this will be a +2 state. So both oxygen atoms have to add up to a -2 state, making each atom of oxygen a -1 state. Oxidation states are always given for individual atoms. And again, if you look at KO2, oxygen in this case has to be -1/2 because potassium is 1. So -1/2 for each oxygen atom, and the +1 of potassium adds up again to an overall state of 0. So now in binary compounds involving metals, group 17 elements, this family over here, always have oxidation states of -1 when they're combined with metals. Similarly, group 16 always will be -2 when they're combined with metals. And group 15 will always be -3 when they're combined with metals. So some examples here. Magnesium bromide, magnesium's +2, so bromine has to be -1. Sulfur in this case, lithium is +1 because it's in this family, and sulfur would be -2. And in this case, lithium is +1. There's 3 of them, +3. Each nitrogen would be -3. So again, I remind you, please practice when the lesson is over. This on page 85, example 3.7, to master the skill of assigning oxidation numbers, because so many questions on your quiz and on your final exam require you to actually assign oxidation states. So redox reactions, again, we're going to talk about how we can use oxidation states to determine what is oxidized and what is reduced, and in fact, whether or not the equation represents a redox reaction. So I'm going to show you now how to use oxidation states to make those identifications. We're going to look at some reactions here. So here's an example. So one of the first things we do is we assign elements that are by themselves 0. Well, we can see copper here is by itself. It's going to be assigned a value as 0. And oxygen almost always is -2 when it's in compounds. Hydrogen is +1 when it's in compounds. So we can assign the missing oxidation states by using the quantities that we do know. So let's start. So copper is an element by itself. It's assigned a value as 0. So oxygen is -2 when it's in a compound, -2 when it's in a compound with other atoms. And now hydrogen is +1 when it's in compounds. Again, over here, +1. And now we can start seeing that, hopefully you understand that nitrate, NO3, 1-, if you remember your rules for strong acids, or if you just remember your naming conventions, nitrate, NO3, 1-, there's 2 of them, so copper is a 2+ state here. And now we're going to figure out the nitrogen in this compound, nitric acid. So each oxygen is assigned an oxidation state of -2. So the overall state for oxygens is -6. Well, if you do simple math, if we know this has to add up to 0 overall, nitrogen must be 5, because +5 + 1 gives us +6. Oxygen total is -6. So we're going to put the 5 above the atom. When we assign numbers for oxidation states, again, they're for individual atoms in a formula. Now, over in this side, we can use 2 methods to do it. For myself, I like to say, well, nitrate, NO3, is a 1- state. If each oxygen is -2, it's a -6. We know it has to add up to -1. -6 added to +5 gives us that overall charge of -1. Or the other way of doing it is to say, well, there's 2 nitrates here, so you could work through and figure out the charge of nitrogen that way as well. But I'm going to go with the simpler method. So in this case, we can see that oxygen is -2. There's 2 of them, -4. Each nitrogen atom must be +4. So now we can see what has undergone an oxidation change. So that's what we're going to go next. So when we inspect this, we can see that the copper has gone from 0 to +2. In order to achieve that change in oxidation state, what must the copper have done? Well, it must have lost 2 electrons. So we say the copper atoms have been oxidized to copper 2+ ions. Now, similarly, if we look for a change, the hydrogens and the oxygens don't often change. Nitrogen is going to change from 5 to 4. So it must have gained an electron. So it went from 5 to 4. A +5 state can only change to a +4 state if it becomes more negative. And it does that by gaining electrons. So we say the nitrogen in the nitric acid has been reduced. Okay. Now I'm going to show you here a little video of this particular chemical reaction. This is quite fascinating. If you take copper and drop it into nitric acid is an oxidizing acid. You will see a fairly significant reaction here. So we're pouring some nitric acid in the flask. Then some copper wire is going to be added. I like to do this when I have pennies, if I want to clean my old pennies, and I put them in for a short period of time. The penny reacts the same way here. Now, we're producing a poisonous gas, NO2, nitrogen dioxide, so This has to be performed in a fume hood, and you can see as the gas escapes from a positive pressure over time, what will happen is the overall pressure inside this flask will start to drop, and the air pressure outside will be greater than the pressure inside because of the release of gas. The gas that's released is dissolving in the water here. So what's happening now is the pressure is reduced inside here, air pressure is pushing down on the water, and you're seeing that as the water enters, you can now see the result of the oxidation. A typical bluish color usually indicates the presence of a copper 2+ ion. So I know that copper 2+ ions are created here from the copper in an oxidation process. So now, other terms we can use, if copper is being oxidized, we can call it the reducing agent. And if the nitrogen and the nitric acid is being reduced, we can say the nitric acid is the oxidizing agent. So nitric acid is a powerful oxidizing agent in this context. All right, so let's move to the next slide here. So we're going to use, again, oxidation numbers to figure out what's happening. We can see that iron goes from a 0 state here to a +2 state here. Again, elements by themselves are always assigned zeros. This is hydrogen by itself. It makes sense when you say both atoms are equally sharing the electrons. So the oxidation state is 0. Same thing here. So we know hydrogen is +1 in most compounds and chloride is -1. In this case, chloride's -1, so iron must be +2. So we can see the iron has been oxidized. We can say it is the reducing agent. We can also see that the hydrogen in this case has the hydrogen in the hydrochloric acid has been reduced, so we can say the hydrochloric acid is the oxidizing agent. Another example, zinc by itself is a 0. Now we'll look for the hydrogens and oxygens. Hydrogens are +1, oxygens are -2. Now, in this case, again, we can figure out what sulfur's oxidation state is by knowing sulfate is SO4 with a -2 charge, because there's 2 hydrogens with a +1 oxidation state. So if I know the overall charge has to add up to -2 for sulfate, I can say that's going to be -8. Sulfur has to be +6 added to a -8 to give us the overall charge of -2 for sulfate. Or I could do the whole compound as 0 and come to the same conclusion. -8 + 2 is +6. So 6 added to +2 gives us +8. -2 times 4 gives us -8. So we can see the sulfate is going to have the same oxidation state on both sides. When ions remain intact, they're going to have the same oxidation state. But we do see in hydrogen sulfide gas, in this case, if hydrogen is +1, then sulfur in this case must be -2. And we can see sulfate is -2 overall. Zinc has to be +2. So sulfur is -2. So now we can see the sulfur underwent a change in oxidation state. The zinc underwent a change in oxidation state. So we can say, in this case, the zinc is oxidized to zinc ions. It's also the reducing agent. And we can say the sulfuric acid in this case has been reduced. It's the oxidizing agent. So again, another acid acting as an oxidizing agent, which is why a lot of acids are reactive. They love to steal electrons from other substances. In this case, it's the sulfur, going from a 6 state plus state to a -2 state. 8 electrons in all have been stolen from zinc. Another example, hydrogens +1, hydrogen, we're going to put hydrogens in here. Oxygens are -2. Now you should be getting a little bit better at this. So we can say if oxygen is -2, the total is -6. Added to +1, nitrogen must be 5 in that case. And over here for H3ASO4, there's different ways of arriving at the answer. But if we go -2 times 4 is a -8 state. and we have 3 1+ states. That gives us a +5 for arsenic, because 5 added to 3 gives a +8, -2 times -4 gives us a -8. And nitrogen in this molecule here, nitrogen monoxide or nitrogen 2 oxide, it's going to have a charge of +2. So we can see again, nitrogen's going from a 5 to a 2. We can see arsenic is going from a 3 to a 5. We've identified since arsenic's oxidation state's going from 3 to 5, in order to become more positive, it has to lose electrons. So arsenic is oxidized, so the arsenic acid is the reducing agent. And the nitrogen and the nitric acid is reduced, so it must be the oxidizing agent, because nitrogen's going from a 5 state to a 2 state. Had to gain electrons to do that. One more example, hydrogen's +1, oxygen's -2. So we can see in this case, sodium is +1, iodine's -1. Now, chlorine in this case, remember the whole oxidation state has to add up to 0 because it's a neutral compound. So chlorine must be +1, because when added to hydrogen's +1 and -2 for oxygen, we get a 0 state. In this case, let's look at iodate ion, IO3 1-, that gives us a -6 for oxygen. So iodine has to be 5 state. So the other way is to simply say the overall molecule, 5 and 1 adds to 6, -2 times 3 is -6. Doesn't matter how you do it. You can either use the iodate ion or use sodium iodate. It's up to you, whatever is easier. So identifying what's changed here, you can see that iodine has changed and chlorine has changed. Iodine's gone from a -1 to a +5. Chlorine's gone from a 1 to a -1. So from that, we can say iodine has gone from -1 to +5. It must have lost 6 electrons. So the iodide ion is the reducing agent. And similarly, the chlorine in the hypochlorous acid is reduced. It must be the oxidizing agent. So now we're going to show you how we can balance redox reactions, a very useful skill. Now, there's 2 methods of doing it. I'm going to show you the oxidation number method, but just because in some cases it's easier, but a method that is usually better for solving more equation balancings is the half cell method, which I'll show second. So we're going to emphasize the half cell method, and balancing using oxidation number method I'm going to show you anyway. It's for information only, but in some contexts it's useful. So when you're using oxidation number method, you're going to get rid of the spectator ions in water. You're going to identify the elements that change oxidation states. You're going to identify all the oxidation numbers, particularly for the reducing agent and the oxidizing agent, of course. And you're going to equalize the transfer of electrons. And then you're going to, if you have to, you're going to balance charge using hydrogens and balance hydrogens. You're going to balance using waters as well. And then you can replace spectator ions if they were removed. So I'm going to show you some examples here using oxidation state here. So, and here's the method for doing this particular technique. So here's the first technique we're going to use is nitric acid reacting in this case. So the oxidation state for oxygen is -2 in each of these. And it's going to be +1 for the hydrogens. And so the total oxidation state for oxygen is -6. The oxidation state for hydrogen is +1. So we get a +5 state. And here we have a total charge here of -6. So hydrogen is going to be +3. So arsenic has to be a +3 state. And in this case, we have 4 oxygens giving us a total of -8. Each hydrogen is +1, so that's a +3. We're going to need a +5 state. And oxygen is -2 and nitrogen monoxide. So it's nitrogen is a +2 here. So we are going to now identify which substances change their oxidation state. So nitrogen is going to go from a 5 state to a 2 state. And arsenic's going to go from a 3 state to a 5 state. So we can see to go from a 5 state to a 2 state, 3 electrons for every molecule of nitric acid were exchanged. And for H3ASO3, arsenic acid, you can see from arsenic to go from a 3 state to a 5 state, there were 2 electrons involved. So first thing we're going to do is balance the number of electrons transferred. So a common multiple of 2 and 3 is 6. So we're going to balance the electrons. So we're going to have to multiply this equation where there is 3 electrons transferred by 2 and multiply this equation by 3. And now since there's 2 nitrogens here, we're going to make, the only place where there's nitrogen is here. So we're going to make 2 nitrogens on that side. Similarly, we need 6 electrons. So we're going to put a 3 in front of this formula to give us 6 electrons transferred. And now we're going to say, okay, let's balance other atoms. Arsenic, there's 3 arsenics. The only place there's arsenic is here, is 3. So we're going to put a 3 in front of that formula. So we've just used oxidation numbers to balance this equation. In this case, all other atoms need to be balanced. So you could check for hydrogens, but it looks like it's balanced. We have 9, 11. We have 9, 11 hydrogens. And check for oxygens, we have 6, we have 9, there's 15 oxygens on the left, we have 12, 13, 14, 15. So everything seems to be balanced. So next one we're going to do here is use oxidation states again. Hydrogen's a +1, oxygen 0, oxygen's -2, hydrogen's +1. And again, we can see that in this case, selenium is a -2. In this case, it's a -4, so it's a +4. We can see oxygen went from a 0 state to a -2 state. So we're going to identify those 2 substances. So selenium is going, again, like I said, from a -2 to a +4 state. So in order to go from -2 to +4, 6 electrons had to be exchanged for every H2SE formula. And for oxygen, we can see 2 electrons were exchanged for each oxygen atom. But in this case, there's 2 oxygen atoms in this molecule. So if there's 2 electrons for every oxygen, the total is 4 electrons for each oxygen. Well, to balance the electrons exchanged, what's the multiple of 4 and 6? A common multiple. Well, it's 12, isn't it? So we're going to balance it by, if we multiply this formula by 2, we get 12. We multiply this formula by 3, we get 12. We now have 12 electrons being exchanged. And now we're going to balance the seleniums. You can see we have 2 seleniums on the left, so we need to put a 2 here to balance seleniums. And we could check to see oxygen. There's 6 oxygens, there's 4. Well, we can see that we're going to need 2 waters to give us 6 oxygens. And we're going to last double check with hydrogen, 4 hydrogens, 2 times 4 hydrogens. The beauty of balancing equations is you know when you write, everything works out. Okay? If there are other atoms need to be balanced, you do it at this time. Now, most of the time, you're probably going to be using the half-cell method. So let's go over the half-cell method in detail. So here we have a redox equation where changing oxidation states are happening, and the spectators have been removed to make this easier to illustrate. So here we're going to separate the overall equation into 2 half-cell equations, an oxidation and a reduction. And the coloring is kind of leading us here. So the manganese, you're going to say, well, the manganese changed from this state to this state. So there's our first half reaction. And the sulfur is changing from this state to this state. So there's our 2 half reactions. One of them will be an oxidation, one will be a reduction. We don't know yet which that is, but let's follow the steps for this method. So first thing we're going to do, we're going to balance atoms other than oxygen and hydrogen first. In this case, this one here doesn't require any changing, but the other half reaction, sulfur, there's 2 sulfurs on the left, there's 4 sulfurs on the right, so we're going to balance sulfur first. Now, you can see that half reaction is balanced. This one, manganese is already balanced, so we're going to go on to the next state, the next step. So we're going to always balance oxygens next. After all, atoms other than hydrogen and oxygen are balanced first. We're going to balance oxygen next. So we're going to now say, oh, there's 4 oxygens on the left. Well, we're going to use water molecules to balance oxygens. So we need 4 waters to give us 4 additional oxygens. Because there's 4 oxygens on the left, we need 4 oxygens on the right. For the other half reaction, we can see there's 6 oxygens on the left, there's 6 oxygens on the right. It's already balanced. From the first half reaction, you can see when you balance the oxygens using waters, you created an imbalance of hydrogens. So now we're going to deal with the hydrogens that we've added. So we've got 8 hydrogens on the right. We're going to have to balance the hydrogens on the left. So in water solutions, hydrogen ions are always present. So we're going to use our knowledge of the chemistry of water to say if there's 8 hydrogens that were added here, we're going to add 8 hydrogens to the left-hand side. So now we can see 8 hydrogens, 4 oxygens, 4 oxygens, 1 manganese, 1 manganese. I always double check as I'm doing it to make sure everything's balanced. So we're going to balance charges on both sides of the equations now to determine again what's oxidized and what's reduced. So for the first half reaction, we can see the overall charge, 8 positives, 1 minus is 7 positive for the left-hand side. On the right-hand side, the overall charge is positive 2. So clearly, there's an imbalance of charge there. We are going to balance it by adding 5 electrons to the left, because when we add 5 electrons to the left, we get 6 minuses, 8 pluses. We get an overall charge of plus 2 when we add the 5 electrons to the left. Why do we need a plus 2 charge? Because the overall charge on the right is 2. So that's our next step. Double checking again. 5 and 1 adds up to 6. 6 minuses, 8 pluses gives us 2 pluses. There's a 2 plus charge on the right. So we have now, we're going to do the same thing in the other half reaction. Our overall charge is 4 minus on the left, 2 minus on the right. So what we're going to do is add 2 electrons to the right. Again, 2 minus and 2 minus gives us 4 minus. 2 times 2 minus gives us 4 minus. So we now have the electrons in our half reactions. And now you can actually tell what's being reduced and what's being oxidized. A gain of electrons, remember, is reduction. A loss of electrons is oxidation. So we can see the manganese is gaining electrons. The sulfur is losing electrons. So next, we're going to balance the number of electrons on each side. If there's 5 electrons gained and 2 electrons lost, the common multiple is 10. So we're going to multiply the first half reaction by 2 and the second half reaction by 5. So when we multiply the first half reaction by 2, that's the result. When we multiply the second half reaction by 5, we're going to get a 10. We're going to get a 5. We're going to get a 10. So when we add both equations and simplify, what can be canceled here? Well, the 10 electrons are gone. So we have 16 hydrogens, 2 permanganates, 10 St2O3, 2 minuses, 2 manganese, 2 plus ions, 8 waters, and 5 S4O6, 2 minus. Now we could check to make sure this is balanced. And we're going to count everything. So the charge, typically, if it's not balanced properly, charges will reveal that it isn't. So when I look at 16 positives, and I have 2 negatives here, 20 negatives here, 22 negatives, and 16 positives give us a total charge of 6 minus on the left. Well, let's look at the right. On the right, we're going to get 4 positives. We're going to get 10 negatives. 4 positives and 10 negatives gives us 6 minus on the right. The charge is balanced. Oxygens, let's check them. We have, if you take a look here, we have 8 oxygens here. We have 30 oxygens here for a total of 38 oxygens on the left. On the right, we get 8 oxygens here, 5 times 6, 30 here, 38 on the right. So hydrogens on each side, so 16 hydrogens on the left, 16, 8 times 2, 16 hydrogens on the right. And sulfurs, we see we have 20 sulfurs on the left and 20 sulfurs on the right. So every atom is balanced. The charges are balanced. We know we did it correctly. So the manganese, sorry, I forgot to check. There's 2 manganese here, 2 manganese here. So jump the gun a bit there. So it's balanced. Now, there's a special rule. If the reaction happens in a base, and you'll be told, balance the equation in a basic solution, you have to get rid of the hydrogen ions if it's in a base. How do we do that? Well, recall the Kw of water. Is hydrogen ions added to hydroxide ions create water. That's always happening in an aqueous medium. So if we add 16 hydroxides to the left side, we're going to get rid of our 16 H pluses. But remember, we're trying to balance this equation. So if we add 16 OH1 minuses or hydroxide ions to the left, we're going to need to add them to the right. So when we do that, notice what we've done is we've added the 16 hydrogen ions, and the 16 hydroxide ions give us 16 waters. On the other side, we're just going to leave the 16 hydroxides. And if you inspect this equation now, to balance it, you can see there's waters on both sides. So now we're going to get rid of the excess waters by subtracting 8 waters from each side. So when you subtract 8 waters from each side, you're left with 8 waters on the left. You're left with 16 hydroxides on the right because the 8 waters are now gone, and you have a balanced equation, which again, you can check to see if it's balanced using the steps I have just carried out. So you can go one by one and you'll know your answer is correct. Now, if you're in a hurry, I check for charge first, and then I check for oxidants, and then I'm almost guaranteed it's going to balance when those two are in balance. So we take a look here. We have 2 minus here. We have 10. We have 22 minus on the left. On the right, we have 10 and 16 is 26, and 4 is 22 minus again. So we look at oxygens. We have 8 oxygens. We have 8, 16, 10, 30. We have 46 oxygens. So 16, 30, we have 46 oxygens. So it's balanced for oxygens. It's balanced for charge. Go further, 2 manganese, 2 manganese. Sulfurs, we have 20 sulfurs. We have 20 sulfurs. So, and hydrogens, we have 16 hydrogens. We have 8 times 16 hydrogens. We know it's correct. Yahoo! All right, there's our balanced equation. Now, again, to master these skills, you must practice. So here are some examples in your course book. Make sure you work through them until you've mastered it. And be prepared to balance equations on your next quiz. So, signing out now. Take care. Enjoy.